Okay. But I won't present in that time period.
What?
The poster's not until like the 22nd of August.
It does matter.
Okay.
Because it's end of the overall whatever. So we send the report in the 6 months after the the final date of the proposal.
Okay. So side question. Since I have a meeting at 4 here, 5 there, could Javed go first? Or is he not ready yet?
Sure, please, go ahead.
Because we don't have Erin and London yet.
Oh, yeah.
Are they coming?
Right. First means right now, then.
Yeah.
Okay.
Thank you, Javed.
No problem. It's fine. It's going to be short and not that interesting, I guess. Yeah.
Who knows?
Because I didn't include the questions.
Javed, I didn't think that CCAST had ADF or no Amsterdam, whatever the one of the programs
That's why
that you had. I thought.
discussing today to purchase this one. Yeah.
Oh, to purchase. Okay, because I thought we had that for like a year and then it expired.
Yes, the keyboard is expired. And the license is only for 1 year. You need to buy a new license
And
every year.
they have a new version too, so.
Oh, a new version as well, so the old will not work
Yeah,
anymore.
they released the new version last year.
Oh, hey, John.
Oh, okay, John.
Hey, John.
Oh, hey.
So did you sign your official paperwork for the new place, John?
I have not.
Oh, you're still
Wait,
thinking?
did you get hired?
Well, my understanding is that you got the offer, right? Did you?
I did get the offer. Yes, I did.
Congratulations with the offer.
Oh, thank you.
So now you are trying to think? You're still thinking about it, or you're just negotiating?
Well, there
balls.
have been some serious discussions with my wife and I.
So, okay guys, so this one I'm going to talk about, it's just actually not I'm going to talk, it's a kind of interactive things. So we are going to buy a new software, but they have a lot of options in the market. They have some free software packages also. So that's why we are trying to find out which one would be better from the all perspective, like price and available feature and everything. So in the first slide, I'm just put the license price. If you look in here, turbo mode price is like $3,500. This one is a license for permanent license, so we don't need to pay yearly or something like that. But it's included for 1 year maintenance, support and updates. So after 1 year, we won't get any updates or any support from them, but we would have a license, so we can use that existing code anyway. And for if you want to get the new updated versions, so there they have one interesting thing is, and they said that after 1 year, if we want to get the maintenance support and update, we need to pay 20% of the license price. So we need to pay 20%. Have any questions, Levi?
No, I don't
I
think.
think it's just.
No, not yet.
It could be a feedback.
Just some noise, but nothing.
So, and if they have any gap for updated and existing license, so we need to pay 20% for each year, or we need to pay for new license, which one is smaller in that case. And for ADF is pretty costly. They have a lot of options for ADF license. They have we can buy for fixed core or unlimited core. They have option also floating core. Floating core means we can use that in any different cores. And for this price is for unlimited core for a 1 year license, 4,500. After 1 year, you won't get anything. So it's fixed for 1 year.
By the way, about GUI, do you remember how many of nodes which have in the graphical kind of type of
Or not.
on the CCast, like which allows this GUI thing?
GUI thing is for local machines. CCast doesn't have X server.
No, I think they do. This is a new, like they were updating it in this group meeting.
Oh, maybe then
user
I'm.
meeting. So he kind of mentions that they have really a very small number of nodes, but they actually upgraded, like when they were upgrading the CCast, they also upgraded for the GUI, or whatever you call it, GUI, right? Whatever the abbreviation.
So GUI software is for just like DOS view for these things here, for visualizing purpose and creating the new software and those things here. They put this one and included. But if we want a GUI for ADF, like DOS view, we need to pay $450 more extra. And since this is a 1 year license, there are no questions about updates and everything. After 1 year, you are done. So in the license price perspective, TurboMold is far better. Now question is the TurboMold has all feature. What do you want to calculate? And this is just a comparison list one. I just few something, and DFT transition is DFT is common, so DFT software and DFT, and for transition state calculations, and I look on the TurboMold so far they have a you can calculate the transition state by this method, transition state reaction coordinate methods, but in ADF they have 3-4 different methods like nudge, elastic band models, eigenvector following methods, and but these other methods also are available in BUS, I guess, nudge elastic band models. I don't know about the other one. And for the most important things, what we are looking for, that's the relativistic corrections on them. And in the ADF, they support the Zora corrections and also the 2-component relativistic corrections. And in TurboMold, they only support the 2-component relativistic corrections.
This is the same as WASP is supported, right? 2-component relativistic effect, or whatever you call it.
It's X2C or something like
How do they call
that.
it in WASP?
Non-collinear.
Non-collinear, okay. It's the same thing, right? Okay. But the difference is that this is really for the time-dependent calculations, right? So, not for the ground state, but you can really add
we can add
effect when you do TDDFT and getting excited state calculations, which again different from.
For Zora calculation, it will support just like ground state energy, and also in TDDFT is included only spin orbit coupling, not the relativistic corrections.
Well, spin orbit is relativistic correction.
I mean, in that, but Zora have
not all,
not all, Darwin or all that effect here. So in Zora, it's only in ground state. In excited state, only spin orbit coupling support. For solvent effect, and they have a lot of different solvent models in the ADF. In the TurboMold, they have only one Cosmos, and but I don't know exactly all of them. I just put this whole list here. For dispersion corrections, and they have a DFT, DFT-D3 methods. But for ADF, I didn't found exactly listed any dispersion correction or not. They have a DFT-D3, I guess, but they have another different software like for DFTB and all other packages.
So in other words, you need to buy another
DFTB,
edition
DFTB package
to include kind of more functionals and more DFT methodologies there. Okay.
So, and that's also like priced like 1,500 to 1,000, I guess, 2,000, yeah, I guess. So, and main
what about the constraint DFT? Is it supported?
And I didn't find specifically they mention anything about constraint DFT in the list.
Neither of them?
No.
Then if they're not mentioned, probably it's not.
Maybe it's mentioned in somehow other list, but they have one list all of the feature, but I didn't constraint DFT. And for basis set, one basic difference of these two.
Well, I would probably say, like, I know I didn't kind of ask you to do it, but there's also another software, NWK, right? Which also kind of allows for calculation of the pretty much the same, and it's free.
Yeah, I look. Yeah, that's I put that information on the next slide actually. So for NWCam and games, both has a Zora calculations too, and both are free software.
But again, it's only in the ground state.
Yeah.
So for TDFT.
And for TDFT, NWCam also support the spin orbit coupling and excitation, spin flip transitions. So it will give us the spin flip transition energy too. And NWCam also has a constraint DFT. So in that comparison, if you compare the NWCam other two, since NWCam is a free, and also we have NWCam in all systems.
Hey, Jabed. Do you know if ADF or TurboMore can do like transient absorption simulations?
Transient? I'm not sure about that. No, I don't think so.
Okay, because I saw a paper which I thought used TurboMore to do transient absorption calculations.
I send you a list of this, a link of the feature of both. Can you go to that link and check on this one?
It is supported in the same way as you were trying to use this with Gaussian. Remember, like from some code for that guy. So even if it's supported pretty much in the same level of theory, which you already know. It's not sufficient, unfortunately. You're not getting enough transitions to get to the visible range. Right? Because it's excited state transitions. If you have very dense spectra, if you have, or your excited states are kind of very dense, the splitting is very small, then of course you're getting the lowest transitions, which are in the infrared and which they don't measure with their spectroscopic properties because they measure only excitations at the visible range, right? So this means you need thousands of transitions, which of course means, again, you need to create a huge matrices, which is just not feasible in this methodology. So even if it does, it probably does. TurboMole is known. I think it was the first software which is doing this. Again, maybe it's in a development version or something, but it kind of should have this feature. But it would be in the same level as you already tried with Gaussian, not better than this.
Sounds good.
And another thing is in the TurboMole, it supports the molecular dynamics, but we have molecular dynamics software bias. I'm not sure, I don't think it's very important here. But ADF is just for DFT, it doesn't support the molecular dynamics. And another thing is in ADF, they have some feature, two methodology to calculate.
But if we go molecular dynamics again, you can run excited state molecular dynamic in this case. Yes? You can optimize the excited state. It's adiabatic, but it's in a, like you can optimize the excited state with TurboMole.
As we do in the Gaussian, yeah, but this one is according to molecular dynamics at the higher temperature, like here.
Oh, yeah.
Okay.
So.
And they have another feature in ADF for calculation of charge transfer, like current flow and other things, by using the two different methods available. One is a green function based method, another one for charge transfer integral methods here. So in TurboMole, it doesn't have.
If they talk about CT integrals, I think it should be constrained DFT then. What is the charge transfer integral? You can create, like, again, the main idea of constrained DFT is that you kind of assign the density, saying that some portion of density should be localized on this part of the molecule, another part of the density localized on the other. And you're not allowing, with this, adding this additional constraint, you optimize the overall ground state and so on, right? And then, of course, you can think about kind of, applying this constraint DFT to the excited state or to any other kind of things. I'm not sure what exactly they mean by this.
And this one, I guess they're doing like, they have some graphical presentation. They're showing something like charge is localized on the two differently localized, and it's transferred through the like bulk or other connectivity, something like that.
So they calculate current.
Yeah.
It's a current calculation.
They
so
also
the interface.
they also for
Oh,
green function method they also able to do the current or charge
Okay.
flow. It's a dynamic charge transfer node here, kind of like that. In other cases, it's almost similar. It's only one thing is not available in thermal, that's the Zora corrections. For this one, as I said, the Zora correction is available in the 2 free software. Both was available in our cluster. And another thing is molecular dynamics have available in thermal, but we have another molecular dynamics software like Buzz. So there have. I was asked to talk about actually the relativistic corrections, about the Zora corrections and the other methods, but unfortunately I don't know any much about either of them. So in that case, in this one I just put the 2 very basic equations for the Zora corrections. So we know that this relativistic correction is coming from the Dirac equations, so they have 3 different parts. So and Dirac equations derive from the 2 component system. So in the first order corrections, I took this original paper, and so these are the 2 functions we need to define based on the 2, and these 2 functions can be related with this operator. The chi operator is it given here?
What is chi?
Not chi. I mean this operator. I mean they have one relation. It's not given here. Whatever. And so for the 2 component, our main purpose is to replace one component by other one, and then found out a Hamiltonian who it will be the computationally feasible.
So what is the difference between phi and chi?
Yeah, one is positive, another one is a negative. In that case, is a one.
What is the interpretation?
In physical interpretation, like electron and positron.
Okay, or electron and hole.
Electron in this case, yeah. In this case, yeah, electron and hole, and they also have a 2 part for each of them. In total, the four components.
And it's 4 because why? Because of the spin, right?
I guess it's not. It's because of its spin, yeah. All right. And this sigma is for polymetrics. There's a potential that have two component phi and chi, and then for some simplifications we will get these equations, and then if this is Hamiltonian, we will get the 0th order regular approximation 0. From here, this is a whole term for Hamiltonian, and then if we approximate 0th order, we will get this first 2 term here. So that's why it's known as 0th order regular approximation as Zora conclusions. So this one, and another thing is they mentioned that this calculation is very specifically based on the selective basis set function. So they have a reasonable basis set in the IDF. They specifically mentioned that for almost all of these elements. And another corrections was the double component corrections, and I didn't put anything on because I went through the theory and there have a lot of things I didn't understand there from here. But one thing is that in the double component is saying that because since they have in Dirac equations derived from the 2 components and the plus minus in total 4 components, so 2 components is converted to the 1 component. That's why it's known as a 2 component 1, exact component to 1 conversions. And these 2 about this them here. So this is a brief comparison between these two software. And we need to decide that either one we want to buy, or we can go to the free software available and WK. games.
Javid, is Turbo installed on NERSC? Did you check?
I didn't check that one.
Again, because it's not a free software,
It's not a
even
free
if it's
software.
installed.
Yes, you need to
If
buy a
someone-
license.
yeah.
The question is, if you buy a license, would you be able to use it on NERSC?
It's a group license, so price is same if you wanna buy here.
No, question just, is it installed there? Because if you don't know it, it's fine.
I don't know the
Okay.
install or not, but if we wanna buy, then we need to buy as a group license too, but they have no discount or anything like that. But ADF, they don't have. If they have, we cannot use because it's like fixed core. Even they have a fixed core and floating core options too. They're very selective too. So that's all from my side. Yeah.
Doesn't look like Turbo Mo's on NERSC.
Oh, thank you.
It doesn't have
And I'm not really seeing anything. that
What was the
points
other
to
one?
that.
ADF.
ADF.
Doesn't look like that's on there either.
Is Amsterdam Density Functional Simulation Package, something like that.
Yeah, it's not showing up.
But it's not a surprise because again, this software requires a license every year, updates. So even if someone installing it, to support it every year with 4,500 is probably too expensive. So that's why it's probably appearing, disappearing, and yeah. Plus, this is of course used mainly for the molecules, which again, I'm not sure that this, again, for NERSC, it's more kind of used for large scale, highly polarizable kind of type of calculations, which again, chemical calculations probably, I mean, calculations of small chemical molecules do not follow to this kind of approach. So what is your conclusion? What do you think would be more useful, let's say, if we have resources?
From the features, I think that we can go for NWChem since we have NWChem as a free.
Well, NWChem is free software anyway. We get in it anywhere, right? So nothing to choose. I mean, by default, they're already installing it on the CCA, so we will have NWChem software anyway. But I'm saying about these two guys, if we have, again, resources, right? So which of them would be useful, or you think would be more preferential to have?
And it seems like ADF is more user-friendly. From the, if I am browsing their website. And
Really?
everything.
Because based on your kind of notes, it's required, like it's having so many options, which means you probably losing your user-friendly
Oh, in that
approach,
case,
because you really need to choose something and you always need to know what to choose. Of course, you always can just go with the default settings.
But it gives us more options, then we can go to more with a more different methodology and whatever. We have all of different options in this case. But TurboMole is better in that sense. TurboMole is their permanent license. We don't need to, if we buy once, we can use the same code for.
Like you said,
Oh, that's one for
It's still
update.
1 year.
After 1 year, we won't get any update or anything. But still, we won't get any support, any update, anything. But we will have a code like Gaussian. Yeah.
I mean, like Gaussian. Gaussian is not
Zero
having
nine.
any limits.
We don't get their update version, but still Gaussian 09
But-
you can use for long term. Yeah.
But I think it was for 1 year. Can you go back?
Yeah, 1 year for maintenance, support, and update version. Yeah. So after
Oh, I
1
see.
year, if we want them update any update or their support, we need to pay 20% of the original price for each year. But if they have any gap, we need to count 3-4 years, or we need to compare with the total price, which one is smaller, which one is lower. We need to pay that 1 year. But we will have this code. We can use this code permanently, original one. But in ADF, after 1 year, everything is gone.
Hey, so any ideas from Los Alamos group, from Levi specifically?
I think I like TurboMole just because you don't have to buy it year after year. The nice thing about ADF is they do spin orbit coupling. However, I thought when Peng was doing spin orbit coupling for like Dr. Soon's projects, which I know that's not the only reason why you would want spin orbit coupling, Dr. Soon said it didn't really change the overall spectrum. Right?
Well, it depends on the complex. And it did. Like we having this much, it provides much better agreement with low energy transitions. Like it's really shifting into the red.
Okay.
Because
I never saw them. This was just word of mouth from her. So she might not have noticed it, or
you can find
it
this
might not have
paper.
been
It was a
shown.
Peng paper published in 2017, I think we published it. And so this comparison is in the supplemental materials, where you can clearly see the difference. Yeah, so the difference is of course small, but this tail, because usually in experiments they have very long kind of tail, which we usually don't, because our peaks, even if we have like weakly allowed peaks at the lower range, right? So they're really discrete, and like you really don't have this nice tail.
Oh, because of discrete.
Yeah, because you have really one or two states with very low intensity, right? But when you include the spin orbits, then you actually have real transitions, which kind of provide this really dying tail, pretty much similar to what they see in experiment. From quantitative point of view, yes. Qualitatively, you see the difference. I mean, backward. Quantitative, in terms of numbers, it gives you the difference. In terms of just quality, it's not very important, but it was for that complexes, right? We still have several things which, and again, we're not talking about absorption. We also want to talk about emission, and for emission, even if you don't optimize the excited state, right? So kind of getting the right splitting rather than just taking a triplet would be more reasonable. Okay, I guess we're done, right? So let's thank Javid. Is there no any other thoughts, ideas?
Okay, thank you, Javid, once again. And next presenter is Roll Over from previous meeting, London.
We should see it really improve.
Before we start, let me attract attention and invite everyone to congratulate Fatima and John on the MRS Advanced that was accepted today.
I guess before I get started, there is one mistake on here that I noticed. I claimed that the E term here is the exchange correlation functional. That's not correct. It's contained inside of that E. It's like the only part that you can choose, I guess. So yeah, I guess I'm looking at perovskites and titanium dioxide. The reason being that they make efficient solar cells.
Well, before you go to your methodology, right? I don't think you really don't need to explain people what is DFT, since you're not really developing new functionals or anything.
Yeah.
So what's the purpose? But what you absolutely need to introduce your dynamics.
Right, yeah, I still gotta.
And I'm not sure that it's really a kind of reasonable idea to put half of your space, more than half of your space, to use for explanation what is DFT, and have really very small, kind of reserve very small space for your time for your dynamics, mathematic dynamics calculations.
So.
And there was presentation from Fatima, right? You were showing some formulas in your presentation last time, right? For your dynamics part, right? So you can probably share.
Respect for the borrow.
Yeah.
Probably just copy paste.
Yeah.
If she would be not against this idea, so you probably can just take your approach and take in your formulas, maybe modify it slightly, rather than just going through what is DFT.
Right. No, I was just kind of trying to work through this stuff and make sure that I actually understood the process here. And I don't know, I'm definitely going to have to be a little bit less verbose with it, but I'm also thinking that it might be a good idea to go 4 columns. Basically leave these 2 alone, do methods as its own column, because I'm going to have a ton of equations to put, and then underneath the motivation I can put the references and acknowledgements. So that might make it a little bit cleaner, a little more efficient in the space usage at least.
But you will not have space then for you. If it would be 4 columns instead of 3, you're reducing the space for your figures, so you will be not able to put this size figures then. Your figures will be...
Yeah, but I mean, I can also
smaller...
squeeze them together, right? I mean, these ones will be much more pronounced once I actually kind of neglect this whole region where there's nothing going on, right? I got room that I can squeeze those together. It seems like I could make a little bit of room. My only concern with that is really this part right up here. I feel like that might get a bit scrunched if I do that, but I haven't actually gone through and done it yet, so I don't know how that's going to turn out. Yeah, so...
Pretend that you are presenting it for the first time. Just give a quick dry run.
So I'm looking at what differences are made by changing the ligands on the titanium dioxide nanocluster. So in one case I have hydroxyl ligands adjacent to the perovskite, and in the other case I have acetate ligands adjacent to the perovskite. If you look at the orbitals here, you can see that there's actually the HOMO is localized on the perovskite, while the LUMO is localized on the titanium dioxide. And in the acetate example, they're both completely localized on the titanium dioxide. So this is not preferable for a charge transfer process. These are backwards, by the way, so imagine that these are flipped around.
Just a second. Am I right? Is that now you're really looking just on 2 systems?
I don't think that I could put more than that on the poster and still have enough.
So technically, you can see that in both systems you have your same surface for the perovskite.
Yes, the perovskite is exactly identical in both cases. The only difference is.
Can you zoom in
Yeah.
It's a type of ligands and maybe number of ligands in your titanium dioxide system.
Yes, and also the orientation of the titanium dioxide nanocluster.
Well, but this again, you're not did you orient it for purpose, or this is how it ends up after optimization?
It started differently oriented, I'm pretty sure. I guess that was a while ago, so I don't really remember exactly. But I mean, even if this one were to be oriented
but
the
again,
same way that this
when
one
you say
is.
different orientation, it means with the hydroxyl you have how many structures you have with the hydroxyl?
What do you mean by structures, I guess?
Well, you said you have different orientations, so you have hydroxyl with different orientations.
Okay, so the hydroxyl.
Or you're talking about different orientations of hydroxyl versus acetate structures.
So essentially, the structure of the titanium dioxide, you basically have like 2 rings of titanium oxide, and then sticking out of these rings you have the acetate groups. They kind of stick out like the rim, but the hydroxyl groups stick out of the face right here. So in the perovskite case, this face is adjacent to the perovskite, but in the acetate case, this part is adjacent.
Okay, so then it's not really that you're looking on because when you say you also look on a different alignment, right? It means you have an exactly same system with whatever hydroxide or acetate, and you just kind of rotate it with respect to your surface in a different angles or different surfaces to see how this orientation will change the electronic structure or dynamics or something like this, right? So this kind of change in the orientation is kind of naturally comes due to the difference in your ligands.
I believe so. I would have to look at the actual original.
So technically you really
geometries
have
that I
just
don't
2
currently
systems to
have anymore.
compare so far, right? Just 2 systems.
That's all I'm looking at for this poster. I feel like it would get horribly convoluted and very complicated to try to talk about anything if I included.
So you have 2 systems which are different with this titanium part. Do they have the same amount of titanium?
Titanium, yes. So like the core of the nanocluster is the same.
Uh-huh.
The only actual difference is so you can kind of see that you have like a titanium oxide ring here and another one down here.
I would say you have better probably representation of your structure on the top panel where you show in dynamics, because orbitals really close everything. Yeah, here, and if you make it even larger, then I guess we clearly can see this what you're talking about.
So in the hydroxyl case, the only real difference in the structure is that down here you have hydroxyls, whereas in this case, and keep in mind that it's shifted like this, you have isopropanol ligands sticking out at the side.
Can
So-
you show what is isopropanol?
Let's see, are any of them here? This guy is an isopropanol right here, that's a clear one.
John, do you approve that it is isopropanol?
Prop is 3 carbons, right? Or is that butane?
Just show it, please show it once again and ask John.
Including the oxygen. Otherwise it would be propane.
Would it be right? Naming?
So like, yeah, there and up.
It's kind of hard to see,
So you've got an oxygen stick
at least
into
on
a
my
carbon,
screen.
and then the carbon branches out in 2 directions with 1 more carbon on each side.
Okay.
So that, I think, should be isopropanol, according to how much chemistry nomenclature I know.
Yes.
Cool.
Approved.
So, if you look at the absorption spectra, they're almost exactly identical. The only difference is that these little peaks and wells here are just a little bit more exaggerated in the acetate case, so you're probably not going to see any real difference as far as the light that's being absorbed. This is just a schematic that kind of describes in a very loose sense, the charge transfer process. So this one is a hydroxyl, this is the acetate. The figure that I had is just in the other order from what I did this in. So in the hydroxyl case, the band edge of the perovskite, or at least the lower band edge, is that a good way to say that? Lower band edge? That kind of seems like that's talking about this part.
Frontier orbitals may be better to say.
Yeah.
Frontier, how you call it?
Yeah, I mean the HOMO
But you
on
even
the...
just the top of the valence band and bottom of the conduction.
that's
Too
probably
long
better.
to say.
Right.
Well, right now you're acting as professional. It's too long, doesn't.
So yeah, the top of the perovskite valence band is higher than the top of the titanium dioxide valence band. So when you do excite a charge and it eventually relaxes to its lowest state on the conduction band, it's going to be localized on the titanium dioxide. So you will actually have a charge transfer occurring after the photoexcitation. Whereas in the acetate case, you don't have that same band structure, so it ends up exciting, but no matter how you really do it, you're going to end up with your electron and your hole both localized on the titanium dioxide. Yeah.
So there are band structure and everything almost, and charge distribution is completely different, but why their absorption spectra is very much identical?
I mean, I would imagine it's because they have almost the same composition and they're in close to the same conformation, or at least the perovskite is, and that's the major light absorber, so...
And static dipole also should be different in the both system because charge distribution is very localized on the acetate system. I don't know, I'm just curious, I don't know why absorption spectra is very similar identical here.
Yeah, I don't know that I could give you a good reason why they're that
But
similar.
they have slightly different gaps, right? I would suggest probably, again, you have this free space in between your figures, you can probably
Right
just
here.
make, you can, if you're not, if you use the same format of 3 columns, probably you can make it a little bit elongate your figures, right? And show the band gap so we can see the difference, because I think last time you were mentioned, or maybe somewhere in your previous presentation you were mentioned that there are slightly different band gaps, they're not exactly the same.
Mm-hmm.
The difference is not huge, but there is a little
No,
bit
but there
difference.
is a difference.
Right.
Yeah.
And maybe for the spectra, you can show with transitions, since you have really just a single line.
Mhm.
You really can show your transitions. which contribute
Oh,
to the
yeah.
spectra.
Yeah, that would be a good
Or
one.
at least you can show the vertical arrow for your lowest energy transition. To show, because if your vertical line would be kind of in a very edge of the spectra, it tells that your low state is optically inactive, right? And then we can clearly see that maybe the first will be kind of inside your spectra, means it's already in this tail, not very active, but at least more active than the other one, right? So up to you, there are two ways. You can either really show in these transitions, and then it would be like vertical lines of different heights, right? They might be too dense, I don't know, maybe they look not very good, but you can play with
I
it.
could at least put like the peaks in there at the very least. I mean,
Yeah, or you can at least show just the lowest transition as arrow, and again, depending where it's located completely in this dying tail, or kind of in a age where it's having some contribution, right? Will tell us whether your low state optically, because I think Jabbat is saying that in case of hydroxide, where you have this, I forgot which one is which one. In one case you have charge transfer
Hydroxide, yeah.
character.
yeah, it's this one that I have.
For your for your homolumen transition. For the other, it's completely hybridized,
Right.
right? So, and we assume that those which is hybridized should be probably more optically active than this completely charge transfer character state.
Yeah, I guess that would make sense.
But hybridization is not the only parameter which dictates the strength of the oscillator strength. It also depends on the symmetry of your wave function, right? Because depends on how this wave function is rotated and overlapping with the electronic, like Hall and electron wave function, right? So if they will be hybridized but kind of at different angles or whatever, right? Due to the symmetry, they might not give you the significant dipole moment.
Okay.
But intuitively, the hybridized state is supposed to be more optically active rather than completely localized on a quantum dot, or whatever you call it, titanium quantum dot and the perovskite.
Okay.
So, and again, you either see it, you might really see this, and we will see that this low state is completely dark in one case, and maybe some maybe not very bright, but at least with some optical activity for the second case. If not, again, it's not necessarily the case, because again, the symmetry of the orbitals is might be despite the hybridization, the symmetry of orbitals might also kill the transition dipole moment.
In the bottom, I mean, the last figure, is that schematic diagram or this quantity vector function?
Schematically, yes.
Oh yeah, it's just a
Schematic.
schematic. Yeah, no, it's not.
Okay, just trying to look on the what is the energy difference on the pink color.
Yeah, I could, because I'm gonna have to remake this anyway, at least to some extent. So I might make it actually to scale or something, but I don't know if that would really be worth it. I guess. So. Okay, so I guess moving on to the excited state dynamics.
But if it's a hybridized state, why your diagram for the hydroxyl? Hydroxyl is hybridized, right?
The acetate has both of the frontier orbitals on the cluster.
Oh,
Yeah, the schematic is like switched around from the way that it should be on this poster.
okay.
Yeah.
Because I was completely confused. So,
So in the next iteration, you will swap them.
Yeah, I just have to either like cut and paste it and try to do it, or just make a new one.
No, just swap. You drag and drop. You can pull figures through the poster, right?
But this is all like one figure, I guess. So I'd have to
But,
like
yeah.
cut it into two,
cut
try
and
to,
paste.
like-
Cut and
yeah.
paste.
but don't forget, because this it's very confusing.
Oh yeah.
Because-
That's why I put this little note right here, so I can't forget.
Well, guess no one will understand. Yeah, swap it.
Yeah.
And cut and paste it much quicker than redoing.
So I guess any other questions on that? So moving on to the excited state dynamics. I guess the ones that I'm showing here are the excitations with the highest oscillator strength.
And can you show now, since we have this spectra now, can you show
Yes.
what exactly is energy you're talking about? Like in these peaks for your spectra. Where do you excite? Second peak or first peak?
I don't know because I didn't go back and look at the actual excitation.
Well,
energies.
again, this might be useful.
Please do, please do.
Yeah, oh yeah, for sure.
Might be useful, and
But,
again, you can
there's
show
almost
the
no time to
arrows
it
on your spectra where you excite, right? You can put against the arrows or some kind of nodes to say, oh, we excited this peak or in between peaks and so on.
And can you finger on the absorption spectra? One of them, just finger.
What about it?
Just finger anywhere. Higher. Okay, enough. There is a peak.
Yeah.
Can you label each peak, which which pair of orbitals contributes to the peak?
Yeah, that shouldn't be any problem.
Good. And then you can, it will, you making a setup for easier narration later. Remember, this labeled peak, it is where I am exciting.
Okay. Yeah.
Having this character, we
So
excite
you
in the
set
time
up
scale.
traps for your hunt, right?
Yeah.
What is the band gap of this system? First system?
Oh, I don't have the.
I can just add up 3 number and give some
It's
idea.
around 3 electron volt, right?
Yeah, they're
Looking on your
pretty
gap.
close to 3. I think this one was just a hair over 3, and this one was like 3.2 or something like that. I'm not really sure. I would have to look again. Yeah, somewhere in there.
But
It's around.
But also recheck your spectra. It looks too similar actually. I think Javed is
Right.
right. It looks too identical. So maybe it's just like what you think is hydroxyl probably is acetate. You just duplicate the same spectra twice. Maybe. Recheck it.
Okay, yeah.
Or
'cause
maybe you plot it incorrectly or something. I would definitely recheck files and maybe redo it very quickly on a GNU plot or whatever. I don't know how you plot it
For
on
the
the MATLAB.
for the poster, or maybe only for your own confidence, do the same these two plots on the same panel, so that they like 2 lines on the same figure, and see if they coincide or offset a little bit.
Okay.
Because right now it looks too identical.
Right, yeah. The only difference that I can really tell is that this
your
valley
DOS,
kind of dips down a little.
yeah, your
down,
DOS is definitely showing much more difference, and it's really surprising to see such a similar spectrum.
I would agree. I
Similar
was
not only in the
very
low
surprised
state,
when
but
I
even the higher
plotted
state
those.
looks very, very identical, right?
Okay, and if your whole energy is 1.2 and electron energy is 1.55 and band gap is around 2.5, total excitation energy is around like 4.7, 4.8.
I guess when you say relaxation energy, are you referring?
Excitation energy
Oh, excitation energy.
is around 4.7, 4.2, 4.
Yeah, I
maybe
would have to
4.8.
look
You can
those
see
figures up
numbers
a little
there?
bit.
It's on the figure one. And then I add to the band gap, so it's around like here.
I cannot see any numbers here.
So, okay, yeah. So the hydroxyl excitation is. Oh, wait a minute. Hold on. Oh, okay, yeah,
So
yeah.
it's excited to the LUMO 13 plus.
Yeah, it's a little over 3. Definitely not 3.5 though. Yeah, they're both a little bit over 3.
Then it's make me confused. Then is if band gap is like around 2.5, or you said more than 2.5.
But your band gap is at 0 Kelvin, right?
Yes.
Oh, okay.
Yeah. This is after
Oh,
running
okay,
MD,
okay.
and then yeah.
It's already at the room temperature averaged over. Is it average kind of over ensemble? Are you averaging it?
Yes, this is using the Redfield tensor.
Which already kind of introduced
Yes.
this idea of averaging over ensemble.
Right. So, I guess keep in mind when looking at this figure that this is actually one of the hydroxyl ones. I wasn't able to get the acetate ones working. I just recently got all of my couplings done for the spin restricted ones, and I was trying to get that to work, but my computer did not like that very much. So, yeah, I guess this is actually a plot of the charge transfer happening in time. So the y-axis is representing the position of the to say that.
Or width of the system or something like that.
Yeah, because I mean, what you do is you integrate over the, like the X and the Y dimensions in the actual model, I guess.
It's
And
projected
then
to the
this tells you
Z
what the
actually.
electron density is at that height. Yeah, I should think of a good way to say that, I guess, because that's. So yeah, when you start out, you can see that there's not really any charge separation happening. You kind of have like electron hole, just kind of layered up in the perovskite mostly, and pretty much neutral in here, which agrees with the picture of the orbitals that I plotted earlier. And as time goes on, you can kind of see the electron shift up to here, and you still have some dark spots or holes down here, or a hole, I guess. And after about 100 femtoseconds, I believe, yeah, it's about 100 femtoseconds, you have a completed charge transfer, where it's entirely localized on the titanium dioxide. This one is also a charge transfer, but that's not for this system, so don't worry about that. That's just more to see what it would kind of look like. You look confused.
Is it both are charge transfer?
This plot is actually from this system. I didn't get this one working
Oh,
when I
okay,
made
okay,
the, yeah, these were just taken from an
Yeah.
earlier presentation. And I tried to get this one to work today with all 999 couplings, and my computer crashed after about 2 hours.
Oh, it's
You mean like it's not the real data, it's kind of a fake data?
It's
Just-
real data.
just-
It's a different excitation over here. All the other stuff in this column is good, but this one is actually hydroxyl.
You just fill the space here.
Yeah, I just wanted to kind of at least plot out where things will be. So, well, I guess I should maybe leave those up there. So I got these ones lined up like you guys said I should, and looks kind of nice. I guess I don't really know what I want to say about it. This shows the energy of the
You kind of-
exciton.
Is it for electron, your top plot, is it for electron or for the whole?
Both. So the bright yellow is electron density, and then like the darker blues are the hole density. So like there's actually a little.
And then
gauge over here.
initial, then where is your electron density at the initial moment of time? Oh,
It's kind of smeared out over the perovskite, so you kind of have it like above and below your top layer, kind of. It's sort of above and below the layers, which
then why is it not yellow?
it's
Why is it not bright yellow? I don't understand.
because it's not really localized in one specific spot.
Oh, it's spread over the all layers.
Yeah, yeah. So if you look at this, I mean, it's kind of smeared across most of the layers. I mean, it's most strongly localized, I guess, in the top layer, but it's pretty well spread out. So it's not really dense in one.
But then I'm a little bit confused with these colors. Can you return back to your color plot?
I'm trying.
Like your holes, they go from dark blue to what? What is your color scheme? To the light green? Like this
So-
is becoming completely doesn't make any sense, right? Because you're going from if you're using different colors
Mhm.
for electrons and holes, right? And you're saying that this change in colors represents change in
Charging.
It's-
charge density, right?
Yeah, I mean, you
So
could call it
then
electron density, I guess, if that was what you were
going
asking.
whole from yellow to blue makes no sense at all, because blue stays for the maximum of electron. Your whole becomes an electron.
No.
This makes no sense.
No,
Physical
blue
sense.
is maximum positive charge, right? Dark blue is
Correct.
maximum
Yeah,
positive.
the darker,
Yellow
like
is
the
maximum
darker blue
negative.
purple is a positive charge. It's the lack of an electron.
So to avoid confusion, you may, I do see that you have added the color bar.
Yep. Yeah. So I've
But
got this
it
part
is-
here, which
You need to
represents
have two
electron
different
density.
color bars.
It is
for
not
your
s-
So you
electrons
think
and
I should
holes.
have?
Two, and it
With
is,
a clear difference in the color scheme.
and this could be not sufficient because people, right now we are spending like an hour,
Mhm.
but actual visitors to the poster will spend like 5 minutes.
Right.
at
Yeah.
most.
It's going to be real quick.
So highlight and write by text. Blue, very positive. Green, neutral. orange negative. Just and make this keywords already colored, like in green font. Like green is neutral, in blue is positive.
Okay.
I have another question on your second image. That's the correct one, right?
Yeah, that one is
I mean,
actually
right
for the
bottom.
acetate. This is the only one that's not actually
Okay.
acetate.
So what is the initial state? LUMO plus 10 and final state is LUMO, right?
Yes.
So what is the energy difference LUMO plus 10 and LUMO?
Not very much. It's
But if you go to the table below that,
I don't actually have the excitation energies on there.
not excitation energy, just they have it listed as a whole energy is 2.91 and electron energy is 0.9.
Those aren't energies, those are relaxation rates.
Oh,
So that's kind
Yeah,
of
H
like the
minus-
slope of this part right here, I guess.
okay, my
More or
bad.
less.
Sorry, I thought it was
Yeah.
there.
So you can write K sub E at this spot. If you tell that it is a slope, just add a label
Yeah.
to help to digest.
That seems like a good thing to do. Because I do have like a lot of room still kind of left, and I'm thinking I could probably put the like the legend as far as these probably right in here.
Yes, and here you can explain color codes by words.
So I guess we'll move on to this part. I guess I haven't really changed these since the last time I showed them, but so what I'm gonna do is I'm just gonna chop out this whole part here because it's not necessary, and then that'll kind of make this whole thing a lot more visible as far as what's actually happening. So, okay, so this axis represents time. So as you move forward in time, this is kind of the height is your occupation of whichever electronic state, and this axis tells you which state you're actually occupied in. So that's, I guess, the reason why these are discrete is because you don't have a continuum of states, you have discrete states. So, I mean, as you can see, as time goes on, the electron is less likely to be found in the initially excited state. I forget which one it was off the top of my head, but it kind of migrates down and down until it eventually is entirely in the LUMO.
Would you agree, or would you consider that this set of figures would go much better before your colored figures?
It could, yeah, because that would actually explain kind of, yeah, that would make sense, because that would give sort of an introduction as far as like which states are kind of involved in this whole smeary bit.
Because when you would add all equations, the equations for these colored figures are just occupations multiplied by some distributions. So the occupations are more like core information.
Yeah. Yeah, that'd probably be a good idea.
And why you plot it to 150? If you plot up to 50, maybe it would be look better.
It's just the way that the script is currently set to run. I tried to, so basically I need to
You can
make
change the axis limit, right?
You click on the figure and then it gives windows to change the axis. If you are still in MATLAB.
These are not saved as MATLAB figures, these are just saved as like PNGs.
But you can run MATLAB again and then modify the figures.
Right, and I tried to do that with the acetate model today with all the couplings, but after 2 hours my computer said no, so I decided to try other things. But yeah, I need to be able to make the red field tensor before I can do this script. Oops. So, yeah, I was not able to get to that today, unfortunately. That was kind of what I had planned. So these graphs are showing the same thing, except instead of electrons, it's the whole occupations. And as you can see, I mean, it's a pretty similar time scale. There are differences, but they're not huge. And then this is some of the data that I threw together really fast the other day. Picoseconds inverse is maybe not the right unit. I just wanted to put something there so I don't forget
No,
to do that
that's
later.
right, that's right unit.
Okay.
That's right unit. But do you see any trends? Can you tell the correlation between excitation, energy, and rate of relaxation? Like if you excite higher, would it relax quicker or slower?
Seems like there's a loose tendency to follow the energy gap law.
Would
I
it be-
mean,
would
this
it-
one should
Uh-huh.
have the highest relaxation rates according to the energy. Well, actually, no, this one. Well, yeah, but either way. I guess this one has the fastest whole relaxation rate, but the electron relaxation rate is definitely not the fastest.
Did you try to plot this data represented in graphical form?
No, I have not done that yet.
Same as Fatima did. Can you try it, and then some trends may become evident,
Yeah.
or may not, but it's worth of trying.
Right, yeah, and that might be a better use of space than trying to cram a table into there. Yeah.
So it seems like if your acetate system is very dense on unoccupied orbital compared to the hydroxyl one, because the energy difference of the LUMO 10 to LUMO is very, very small in compared to the LUMO plus 13 to LUMO in hydroxyl.
Right, yeah, and if you look at the density of states, you do actually have quite a bit more going on in the conduction band here.
So
This-
what
and you
about
got,
the
like, a sharp
relaxation
peak right
rate?
off the
So
bat.
isn't it, if band is highly dense, so isn't it supposed to be relaxation rate shouldn't be higher than compared to the other one?
I would think that if you have a higher density of states, the relaxation would go quicker.
Bigger, yeah.
Yeah.
But in the table is showing then the other one is a 1.29 and this one electron is 0.9, smaller than other one. I mean acid hydroxide.
Yeah, I guess I don't know why the electron relaxation rates are slower for the acetate. I mean, the whole transfer rates or relaxation rates are definitely a lot quicker. They're significantly faster. But I'm not really sure exactly, I guess, like what physical reason there would be for these to be slower. Oh wait, and actually,
Is it
now that I
number,
think about it,
number
the whole
you switch
relaxation
the
rate
number?
should depend on the valence band, which doesn't really look a whole lot different.
Whole density is almost similar in compared to these two figure, yeah.
Yeah, there's really not much difference.
Is
in
there
the
any
valence
chance you switch the
Whole
number?
density?
So I mean,
The
what-
valence
what-
band
what-
density.
Wait,
not whole density, sorry, yeah.
So, like, the structure of the valence bands are almost identical. I mean, it's kind of the same thing as with the spectrum.
So for
Actually,
valence
like
band,
the
it
spectrum.
should be approximately the same for both models. For electronic, for rate of relaxation of electrons,
Mm-hmm.
it's about a picosecond. But for the holes, the acetate model is about twice as quicker. Probably because the hole states are localized on titanium dioxide, where there are a lot of nuclear degrees of freedom from ligands, and they facilitate relaxation.
Yeah, that I would agree with that. So, I guess I will move on to the conclusions that I drew from the data that I showed here, at least. So, I guess I don't know if you can actually see it or not. Yeah, you can kind of see it. If you look at the very edge of the perovskite and the in both models, you can see that this one is actually slightly attracted to the titanium dioxide, whereas this one is repelled a little bit. So that would probably make this the more stable model, which would be much better for solar cell applications because you don't want it to degrade over time.
By the way, what are the binding energies?
I don't know.
But you did try to compute them in the past.
Did I?
Okay, you can.
I honestly don't remember. Is you talking about binding between the perovskite and the nanoclusters? And I don't recall calculating that at any point, but I guess I don't really know for sure if I did or
Have
not.
enough time to do it.
Yeah, oh yeah. Yeah, this is still kind of, this is just sort of like where things are going to be, how things are generally going to look.
Maybe you already mentioned that, maybe I missed somehow. How many hydroxyl group and how many acetate group in your system? How many?
So there are 3 hydroxyl groups. Okay, so like each little like ring of the titanium oxide is 3 titaniums and 3 oxygens. So you basically have 1 ligand sticking off of each of the titaniums.
Okay.
So you'll have either 3 isopropanol sticking out like the size of the wheel shape, or you'll have 3 hydroxyls, and then are there 6? Yeah, there should be 6, I believe, acetates in both models sticking off the sides. Oh wait, that's not the one I want.
Would you let me to talk to John for a second?
Yes.
John? So the model that Vanden is using is one of your models with polyoxytitanate with titanium 6, coordinated by 6 acetate groups and 6 isopropanol groups. And later on, 3 out of 6 isopropanol groups were either removed completely or replaced to hydroxyl groups. So you can make any comments or suggestions to London based on this.
Well, so one of the things I had done was initially take this small polyoxytitanate cluster and remove these ligands one by one from the titanium sites and recalculate the energies. So you could look at how binding energies of, you know, a single ligand versus 2 of them versus 3 would give you some type of total energy change. And so you could look at just your single polyoxytitanate with all 6 of the same ligands, calculate it, run a single point with 2 of them removed, calculate it, and then you could rerun a third system that has these 3 hydroxyls pointing down towards your surface. And so you would have, you know, the effect of these hydroxyl ligands on the total energy of your polyoxytitanate cluster. And then you could just run the slab by itself, compare those energies, and then you'd have binding energies for all, you know, 2 of these different clusters and the surface.
Okay. Yeah, I definitely never did it like that if I did ever try to do it. So, if you look at the band structure, which is that schematic that's right over here, that suggests that the hydroxyl will be the superior model again, just because it actually encourages charge transfer instead of, I guess, fast recombination. The electron relaxation times, which are kind of the ones that are more important in this simulation, are slower for the hydroxyl model, which is, again, a good thing, because that means that it'll take longer for charges to recombine, which would hurt your efficiency. So you want longer lifetimes. And then the whole relaxation times are quicker for the acetic acid. Wait, are they? Yeah, they are, yeah. I think that I spoke there. Yeah, I did. Oops. Unless I switch these dates around.
But you can double check it.
Yeah.
For the next time.
Right.
If there will be a next time.
Yeah. Yeah, I think that I got these backwards. Oops. But, yeah, I guess that's kind of...
I have conceptual question about your conclusion. So, like you saying, the hydroxyl ligands lead to longer electron relaxation times. My understanding, I would probably rephrase it slow electron relaxation period. Right?
Yeah.
So longer
that would-
time means it's slow.
Right.
So, and then meaning longer exciton lifetimes, which is favorable for solar cell applications. So the last part, right? So meaning longer exciton lifetime. But the second part, I mean the very last point, is that acetate leads to slow hole relaxation, which
Yep.
means holes are much faster in hydroxyls.
Mhm.
Exciton state includes both electron and hole,
Yeah.
right? So your electrons live longer, but your holes live shorter.
Mhm.
So the exciton by itself probably is not really living longer. So I would probably rephrase this excitation. It just means that you have your electrons living longer, nothing else. Not if you have slow both in electrons and hole dynamics, then you can say, yeah, overall exciton life is much longer in this system rather than in the other system.
Yeah.
But you have electrons is less than twice faster, but holes, I mean slow, but holes more than, actually twice, like in some configurations, it's really twice faster in the other system.
Just be careful with the word exciton.
Yeah.
People like Professor Krzyzewski and his former or future students will give you a hard time if you use it in a wrong
I would
context.
definitely rephrase this last meaning, if you want to really have this meaning, so take out long exciton lifetimes, right? So
Yeah.
you already said that your relaxation time is longer, is slow. So, and then say which might favor the electron transfer processes to the leads, right? Because your electron not really resulting back to the low state,
Mhm.
but can kind of transfer it easily before it's reaching the lowest band, right?
Yeah.
To the, if you have contacts, to the contacts. Or take it out completely. Because I would say it's not really true to say that it's really favorable for solar cells,
Yeah.
since your holes are much faster.
Well, it would be the slower one that would determine it, though, right?
Well, you didn't compute it lifetimes. You didn't compute the recombination.
This is my
of
another
electron
question.
to
Did
hole.
you calculate recombination times?
No, I
Or
think
you
did-
just making this assumption?
You have the data. Maybe you don't realize it, but in the data that you possess, this data is included. But you
Okay.
didn't bring it up and you didn't analyze it.
Would that have been in the same script that got me, like, oops,
Just the.
all of these figures?
No.
Okay.
If you look on the Redfield tensor, which you also can show here in poster, the element corresponding for relaxation between HOMO and LUMA, it will be
Giving
the
you rates for your
recombination.
recombination times.
and it will be substantially slower than all others. All
Okay.
others are like of the order of 1 inverse picosecond, and this one will be of the order like 1,000 times smaller.
Okay. Yeah.
And again, go back to your table, just like maybe a typo or something. If you use K here as rate,
Yeah, that's what I'm
then
thinking
the
that I might have
units
switched
should
these
be not in
papers around.
picoseconds but reverse picoseconds.
Oh, yeah, I
Or
kind of
if you report in time, then
probably
He-
threw in
he's
a little
showing-
inverse.
It is minus first.
Green version is
At
different.
least
It's
in
not
this
easy.
it is C.
I threw in a very crappy little,
Yeah, in
like,
slide
minus
there
one and
are
just
big
copied
parts
and
there.
pasted it.
Okay, here it is not, but
In green version is not.
so it's rate for sure. It's not time. It's not 1.29 picoseconds. It's one. It's It's
yeah,
rate.
it's right. So when you're
so to get the time, I need really to take 1 divided by 129 and get the number for the time.
Mhm.
1 divided by.
yes.
Oh, to get the characteristic time. Yeah.
Yes.
Yeah.
Okay, so then it looks like in all cases you getting something really sub-picosecond relaxation rates.
Yes.
Mhm.
And even like in some cases you have more than 2, so it's actually less than 0.5
Yeah.
picosecond.
Yeah, for the holes in the second table, It is like 300 femtosecond.
Is it reasonable to have sub-picosecond time rates for the relaxation in these systems? Because my understanding that usually in a, well, at least in a semiconducting quantum dots, it's picosecond range, actually. Yeah, not sub-picosecond, picoseconds, up to 10, from 1 to 10, right? Pretty much the same as in the semiconducting materials, bulk materials, not very different.
Just
So I don't see the reason why. Is the dynamics much slow in perovskite, much faster in perovskites, or what?
it's not much. Just
Is it really sub-picosecond range for perovskites? If you just look on relaxation and bulk. And again, this is Oleg Prejda probably has already published this data. in
let's ask John.
Or maybe John already calculated it.
So in your
Yes.
paper with perovskite quantum dot, what is the cooling, electron cooling rate and hole cooling rate?
Well, in the quantum dot, it
Yes.
was more than a picosecond. But in some of the bulk calculations from literature, they were measuring on this, time scale of a few hundred femtoseconds,
Hundreds.
Few
hundreds of femtoseconds. Yeah.
So you having again a problem then, because your perovskite is a bulk here.
Yes, yes, it is.
So few hundred femtoseconds, and it should be.
And your hole is on a perovskite in both cases.
Yeah. So I mean, they had relaxation for holes and electrons at like 450 and 700 femtoseconds on like some of the initial time scales for relaxation.
400 femtosecond?
Mm-hmm.
So it's a sub-picosecond range.
Yes.
Ah, okay. So then it's comparable.
Yes, I haven't read
It's a right order
those
of
papers, so
magnitude.
I don't recall seeing these rates for a similar system to what I have, I guess, so I don't know.
Well, with quantum dots, again, you look just on the titanium dioxide quantum dots, probably people also have data on this from calculations or experimental. And since your hole's really localized on the perovskite, then relaxation of hole should be pretty much similar to the perovskite, regular perovskite systems.
Yeah.
So again, something nice to compare, especially with experiment. And if it's really in agreement, it would be a very strong point because this immediately justifies your approach.
So I'm just wondering one thing about your model. So I don't know the 3D conformation of your system. Is it possible to make this system to connect it to the more number of acetate ion instead of one?
You could. So if you kind of look at, of course, I left the cursor in the way.
So, is it really one, or it's more than one molecule?
It's
at
kind
a
This
time?
one is pretty much just the one that's pointing straight down at it. That's how it
How
ends
is
up
your
relaxing.
3D conformation? Is it possible to make it like?
Yeah, so you have another acetate right there. So that would be, what, 60 degrees, I guess, between these two approximately. So you could get them both down kind of, they'd be sitting more on like the edges of the perovskite, which I guess wouldn't really matter that much because the perovskite is just it's a cutout of like a slab.
But that could change your dynamics maybe significantly, maybe. Yeah?
It could, yeah. I do not have one of those set up in VASP right now though. Or on NERSC.
More questions to London?
John had a question. Do you have a RRR image?
I do have some, but not on here. They're buried somewhere in my hundreds of emails.
Can you dig it out and place it here?
I could try to, yeah. I'm gonna try to calculate new ones anyway, because I'm gonna try to redo these with all the coupling files now that I have them. If I can get it to work.
The other question I had, so when you mentioned that you have basically your perovskite surface pulling up towards this quantum dot with the hydroxyls,
Yeah.
it looks like there's a clear interaction between the ligands and the structure of the surface.
Yes.
Did you ever watch like your actual dynamics videos to see once if it's just something where, they're fluctuating back and forth, or if you would let the optimization run longer, is it something that like the entire polyoxide with the hydroxyls would then just kind of suck back down and the surface would level off. I mean, the bond distance would still be closer, but it would just be sort of even out.
I guess I didn't look at the videos, but I am also doing NCL calculations on these systems, and they're still doing the same thing with non-collinear spin, I guess, as I keep kind of refining it. So, and I've seen at least multiple snapshots of those as I've been going. Speaking of which, my hydroxyl one keeps crashing on that, so would you be okay with helping me with that? Thanks.
More questions? If no, let's thank London for presentation. Please collect feedback and try your best to implement it. Just go around and say thank you to everyone.
Thank you.
And we do have one more practice talk. It is a practice for the actual talk rather than poster. So
we have it all.
you will have the 15 minutes.
How many?
15 minutes for talk plus questions.
Oh, so it's actually 10 minutes question, 10 minutes talk.
Might allow you.
15 or 20 minutes?
Actually, no,
Yeah,
it's my
yeah.
Google Drive.
Like how many minutes?
15 total.
Total 15.
So this one is not the latest one?
No, I upgraded a little
Okay.
bit.
Do you want that someone is really kind of take care for your time?
Probably
Yeah,
to
be helpful.
and maybe also for each slide, like break it into the minutes for each slide, so he knows which slide is a killer of time or which one is really good.
Hello everyone, my name is Aaron Forney. I'm a graduate student at North Dakota State University, and as a title kind of lays out, I'm going to be talking about an atomistic study using DFT about photophysical and excited state dynamics in lead halide perovskite nanocrystals, because recently we know nanocrystals, or lead halide perovskites in general, have been used for extraordinary electronic properties for technological devices. The nanocrystals in particular have a great light emitting applications, but my favorite part about them is that they're funding me through my PhD, basically. So anyway, so this is just an image of the atomistic model that we have for our quantum dot, which we'll go into a little bit. And these are the observables that we calculate for each of the models that we compare them to experiment. And overall, since we can get a radiative and non-radiative relaxation, we can get a theoretical or atomistic photoluminescence quantum yield calculation from our calculations. So, first part of the talk will just be going over how we constructed a model for our quantum dot, because based on different sizes, you can have different surface compositions and different termination ligands, and then just briefly comment on the ground state electronic structure that we calculated for the model. And you can see, did I put it in the other image? I can't remember. I guess I did. So basically you can see that the perovskite part of our quantum dot is basically 2 by 2 by 2 unit cell of the lead halide perovskite, and it's fully inorganic, so it's cesium lead bromide, and we terminate it with the carboxylic or short chain carboxylic acids for the leads, and then alkyl ammoniums for the lead bromide terminations. So yeah, this basically just kind of repeats some of what I said. And then so for the carboxylic acids, they terminate to the leads on the surface, so all these gray atoms. You have oxygens that coordinate to passivate those, and then for systems like these, it's common that alkyl ammonium anions or cations will replace the surface cesiums, and then in the literature has been kind of reported that they're kind of correlated ligand pairs. So if you want good binding of your carboxylic acid, you need addition or a surplus of amines at the surface. So it's a justification for why our model makes sense. And I gotta start sending these as PDFs. My density states got kind of flipped around. But the highlights from this is we use DFT using VASP calculations, and we use PB functional. So it's kind of generally known that if you use GGA, well, without spin orbit coupling, GGA and DFT gives like the correct band gap for the size. But due to spin orbit coupling, we get a smaller band gap than what you'd expect for a nanoparticle this size, which is about 1.5 nanometers. But coincidentally turns out to be pretty much the band gap for experimentally synthesized perovskite. So it's so it helps for our model anyway, that we have the correct band gap. Oh boy.
Yeah, it looks like they're all converted.
Yeah. So then I was going into a transition about so we generally know what the atomic orbitals for the perovskite, so the conduction or the valence band is made up of the halide p orbitals and the lead s orbitals, and then the conduction band is usually a hybridization of the 6p antibonding orbitals. But I guess it's generally not known or assumed how the ligands contribute to the electronic density states. So here is a partial density of states, which I'll flip, which shows where the ligand contributions show up.
You need to click and
Zoom out, and then it is easier to.
What's the zoom?
Yeah. But we can use our imagination to follow your story.
Just
Yeah.
use words.
You can invite everyone to lay on the shoulder and watch the.
So I guess you can see for the valence band anyway. So near the band edge, which I would have labeled B here, that you have, so the black line is the total density states, and then the colored lines are projected density states for different orbitals. So for our valence band, the red is the bromide 4p orbitals, green is the lead 6s, and then these pink I refer to just as ligand states, because if you add too many of the oxygen and carbon, it gets kind of convoluted. But you can see in the conduction band edge that there's this so-called confined hole state, people refer to it in the literature, and then that's composed of primarily bromine 6p with hybridized with lead 6s orbitals. And hiding behind it, you can see that there's a little bit of hybridization with the ligands. And in this par charge density of the quantum dot here, you can kind of see that. So if this is like your terminated p orbital, and then this is like the oxygen hybridizing with it. So that's the little bit of hybridization that's occurring in the state here. If you go further in the band edge, it follows that same trend, and then about an EV out, the 6s states start to go down, and then the ligand contributions start to go up. And those, I guess I haven't fully looked into it yet, but I'm guessing that they're bromine amine orbitals, because since the lead states are going away, like you wouldn't have carboxylic acids binding to the surface leads. And conduction band, it's basically 6p orbitals like make up most of the states for within 1 EV range, and then past an EV, there's a skyrocketing of ligand states that contribute mostly in that region of the states. So we have the ground state electronic structure, and we use that as input for our dynamics calculations. So first I'm going to be talking about hot carrier cooling, where we can get our K cooling rate as after we do a photo excitation in the system. So we excite based on oscillator strengths, which I haven't talked about yet. And then we can calculate the cooling rate from the photo excited state down to the band edge, and then from the band edge, we can calculate the non-radiative relaxation rates. And to do this, we do it using an on-the-fly procedure. So we do molecular dynamics, and then along the molecular dynamics trajectory, we compute non-adiabatic couplings between states, like on the fly. And we use spinor orbitals for this, which is like our computational highlight for this work. I could have a better transition there, but so basically, to describe the computational aspect that we contribute, or the updated part that we contribute to this, is we introduce spin orbit coupling into the non-radiative relaxation. So just to highlight, or give a brief highlight of how what makes this different is, if you consider like a closed shell configuration, you consider like non-radiative relaxation from LUMO +2 to LUMO, you have 3 possible transitions. You have LUMO +2 to +1, +1 to LUMO, and then +2 to LUMO. And say if you're dealing with something that needs to be spin polarized, like transition metal, you would want to do spin polarized calculations to get your electronic structure. And basically you have the same outline because these are spin conserved transitions for spin polarized calculations anyway. So basically you still have the same transitions, you just have double of them. So instead of 3, you get 6. And if you do non-collinear calculations, you can get possible spin flip transitions between all the states. So effectively what you do when you do non-collinear, or include non-collinear into your excited state calculations, is you effectively increase like your density of states window. And generally when you increase the density of states, that's going to impact the non-radiative rates because it gives you additional pathways. And if you take this chart here that we outlined, you can characterize each of these transitions into a matrix like we've shown here. So both of the axes are transitions between LUMO orbitals. So LUMO +0 to +0 is nothing because we just define that as a transition to itself is 0. But then you can do LUMO +1 to 0, which would, in a spin polarized case, would be spin forbidden. But in NCL with spin orbit coupling, that opens up that transition. And then you can also have spin conserving, or what would normally be spin conserving +2 to LUMO, or +3, LUMO +3 to LUMO +1. And you can do the same thing throughout the whole table. But then if you take this chart and you just rotate it, and imagine those bars are amplitudes, those will give you transition rates, like a 3-dimensional matrix, or like a tensor, describing relaxation rates for all the states. So this chunk up here is basically transition between all LUMO states, and then this square here is same idea, but it's just for HOMO states, or whole occupations. And we compute them using state-to-state transition. So basically we take our non-adiabatic couplings from a trajectory, do autocorrelation functions, and then take Fourier transforms of them. And essentially that gives us our non-radiative rates between states. And just from doing that, we can get our non-radiative relaxation rate from across the gap. And our calculations give us about 0.84 inverse nanoseconds. And I don't know, I was looking in literature, I couldn't find a lot reported on non-radiative relaxation for nanocrystals, like direct measurements, but there are people who do, they do photoluminescence quantum yields, and they compare before and after. So if you have 100% luminescence quantum yield, you can kind of backtrack and estimate what your non-radiative rates are. And they estimate them to be within this range, depending, like 0.001 to 0.01 inverse nanoseconds.
So much slower on experiment.
Yes, for if you have a good emitting quantum dot or something with low surface trap stage.
But on experiment, the LQ chains are much longer.
Yes.
I'm not expected to introduce anything to the structure.
But
your low state is optically active?
Yes. So I guess compared to experiment, our non-radiative relaxation rate is a little bit high, and I guess I do have one theory behind that, which I'll get to at the end of it, well, one explanation why, for this system anyway. And then you can also characterize certain trends within the Redfield tensor, but basically, just to highlight is, if you have degenerate states, you have a resonance condition, so you have fast transitions, and anything not resonant, you get you have slower transition rates between states. So if you just project like this, the possible homo states into 2D, this is kind of what I'm talking about. So you have fast, degenerate, and then slow, non-degenerate states.
And for your, this is again the rates. You're getting this 001 to 01.
This number here?
Yeah.
Yeah, so this is,
If it's rates, then it's again should be not nanoseconds, but reverse nanoseconds.
The
Right,
period
they-
should be
it
read
should
like
be-
divide symbol.
yeah, that should be divide. That was probably just a typo. So that's, yeah, that's definitely one, that's inverse nanosecond. And so these provide transition rates between all of our states, but we also have to define an initial condition, because since we're doing a dynamics, we have to specify where we start from. And this kind of turned around again, but basically, based on oscillator strengths, one of the strongest transitions from this peak here to about half an EV into the conduction band. So, which are labeled, so our whole initial state is HOMO -9 and electron state is LUMO +10. And so for this green figure here, this kind of outlines the energy relaxation of the perovskite quantum dot after photo excitation. So you have a photo excitation, electron, LUMO -10, HOMO -9. And during the trajectory, it's you have different energy occupations. So these orange colors indicate increase of energy occupying these states, and then this blue line indicates like decreasing of whole energy in time, and then the black lines indicate expectation values of energy in time. So for this analysis, we assume we can fit it to a single exponential rate, which for systems like this is probably not the best case, because like we introduced earlier, we introduced spin orbit coupling, which introduces additional relaxation pathways. And you also have organic-inorganic interface, which is going to, it's not going to follow the conventional gap law, because it's not a single material in itself. So, well, before I move on, so just to comment on our computed cooling rates compared to experiments. So the couple experiments I've seen reported for cooling rates, they both give about 300 inverse picoseconds, or not 300, 3 inverse picoseconds.
Which will correspond to about 300 femtoseconds.
300 femtoseconds, yeah, they're both important. And those are pretty close for our electron hole cooling rates for these systems too, with same order of magnitude.
So its error is about like 50%.
But you talk about different size in this case, right?
Different size, yeah. They
They
deal
have
with
much
like
larger.
bulk ensemble, and this is a 1.5 nanometer.
And the experimental? What's the radius or
So the
diameter?
word reported means experimental.
Yeah, experimental, and they
How big their systems?
probably like 9 nanometer.
Oh, wow. So it's
So there's a size difference, but I guess the biggest difference between these systems would be the surface coverage of ligand. And I guess electron density too for homo-LUMO overlap, but if you assume that they're confined, like independent of size, they should have about the same if they're passivated.
But confinement actually should be dependent on size. If it's not confined, then there's no confinement effect. I mean,
Right,
if there
I
is no
guess-
size dependency, it means no confinement effect.
I guess maybe I used the wrong language, so like
Well,
the charge is spread out
in
more,
a
but you
quantum
should.
dot language, right? So people usually say whether it's really confinement or no confinement, whether it's in a strong confinement, medium confinement, kind of intermediate regime, or no confinement regime, or weak confinement regime, right?
Mhm.
So they consider the size compared with a so-called exciton Bohr radius, means the size of your exciton, in other words, right?
Mhm.
So I don't know is it the same language applicable here, because again, electron hole pair is considered more like a free electron hole pair, right? Not very much coupled, not very strong.
Mhm. Which would simulate like bulk or like large nanocrystals, because at like 9 nanometers they're weakly confined or intermediate confined.
So when
What they call in the report. So there's
So it means the size of like exciton Bohr radius is something around
So it's 7
10
nanometers.
7 nanometers.
7
so it's
nanometers
really
for
big.
these
okay.
systems, yeah. So it's not a gross approximation to use independent orbitals for cooling rates. So there's not a big excitonic effect. For the ones they looked at in the literature anyway, if they look at an ensemble. And so I put it in a slide because I know we've had a lot of debate about single exponential fits for our data. So I took, oh man. Hopefully I can get. There we go. So it's not going to look as pretty, but we can kind of get the same idea. So what I've plotted is exponential fits for our dimensionless energy during the relaxation trajectory. So that's the top panel. And then the bottom one is like the PDOS occupations in time. Oh, that cut off. And then this figure was supposed to be the density of states that were part of the transitions. So basically what we can see is, so this is a photo-excited electron, so this corresponds to this yellow curve here. We just normalize it so the intensity, x intensity is 1. So the black curve is what we computed for energy relaxation along the trajectory, and then the red dotted line is a single exponential fit. And so we can glean a couple of things just from comparing our computed results relative to that single exponential fit. So we can see that earlier in the trajectory, it's about slightly slower relaxation, up to like 0.7 of its energy. And then in this region here, it starts to pick up or go, like increase faster than single exponential fit. And then near the band gap, like this tail goes on to slightly above 0 or 1 peak per second, because this is log scale. So you can see the closer you get to the gap that the relaxation dramatically slows down. And I tried to correlate that with like where the electron density is occupied in time. So this pink line is the PV success orbitals. So this is like the inside the perovskite. And these two lines here are the only other two states that provided significant electron density. So it's the carbon 2p atoms and then oxygen 2p from the ligands. Here we can see, this was scaled correctly before, that there is a little bit of electron contribution, like up to the point where this fast relaxation happens, or this density starts to dissipate at about the same time that this dissipates. So it seems like that there are some, I don't know what the words I'm looking for. So there are vibrational modes from this aspect here that help drive quicker relaxation.
So this time resolved PDOS of which orbital or which range of energies?
So this is the electron, and this is from...
No, the lower this one.
So this is over the same exact trajectory.
For which orbital or for which range of energies? What are the lines?
So they're basically occupations. So I took occupations of bands, and then I projected the band, instead of it being occupied in one, it's just partial occupations. So like say this is HOMO, initially it's...
So it is occupation of each orbital weighted by P projection character of
yes.
the same orbital. Okay.
So at the initial excitation, you have a little bit of less electron density on the 6p orbitals, and a little bit more. So this is our initial condition, LUMO plus 10.
Okay.
And along the trajectory, it relaxes to LUMO, where electron density comes from the ligand, like back into the quantum dot. It's not highly resolved because there's not a lot of, there's probably only 3%.
Okay, so at a latest stage of relaxation, ligands contribute less to the process.
Right, and my thinking was that whatever the electron density occupied on the carbon, like it's getting some either carbon stretch or CO stretch contributions to the non-adiabatic couplings. And that's what kind of drives the quicker relaxation here. Because I've done this for a couple of initial conditions, and this is the only region where I ever really see quicker relaxation relative to the single exponential. And that's really the only occupation where there's been significant electron density, like not on the oxygen, but on carbons of the ligands. And then there's just the other note too. So in this region down here where there's the really slow relaxation, that's been observed experimentally. It was for a different system, it was for iodine based, but they observed within 0.2 EV above the conduction band, there were spectral signatures like later in time. So it indicates that there was a buildup of electron population, which is kind of what we see here because it's a sparse density of states, so it's probably like 0.2 EV, like subgaps due to the strong spin orbit coupling in the conduction band. So yeah, if it looked really nice, it would have looked a lot better, but hopefully it would have made more sense. So, and then this is just visualization of everything I've been talking about for the past 5 minutes. But I think this link is, this video works. Oh, the video must be saved on this desktop.
No,
So it's now more than
well,
21 minutes.
Well, I tried it earlier on my computer and it didn't work.
It's changing.
Yeah.
But anyway, so this is our initial condition, LUMO plus 10 and HOMO minus 9. So the LUMO plus 10 occupied states are like the orange or reddish orbitals. They're contributing on the outside, so there's like 6p. And then the blue orbitals is like your bromine p orbitals. You can see the holes, there's a little bit of hybridization on the ligands. And this is what I was talking about earlier with a little bit of carbon, or electron density onto the carbon, helps promote the electron relaxation. Because you kind of see it's hybridized with this 6p orbital. So as we progress this video forward, so you can see some of the states changing, and here you can see electron migrating, or the density migrating from the ligand, and everything kind of comes back into the center of the perovskite, where this transition here is like electron density going into the central lead, which is a 6s orbital, so that's why it looks spherical. And then on the edges you can see the bromine p orbitals occupied, and then for the electrons are occupied on the lead 6p. I tried to update it so that it would like partial charge density like along the trajectory, but I wasn't able to get that done for today. And I had intentions of filling this slide out more, but I didn't get around to it. So basically this is just getting our K radiative so we can complete the 3 observables we were looking for. So we use basically Einstein coefficients to get our, those give us relaxation or radiative recombination rates. So you can get lifetimes from just taking the inverse. And we do this with spin orbitals too, so our transition dipoles are computed in a spin orbit coupling basis. And I haven't filled this chart out either, but basically we can compute time resolved emission along our excited state trajectory, which we described earlier. So this is describing radiative relaxation across the trajectory. So initially at time equals 0, we have a photoabsorption. And then at early stages of the time, we have low energy transitions, which give off just infrared heat to transition. And then eventually the system relaxes to the band edge and you get bright PL, which is this line here, where it starts to emit. So this integrates the time resolved. So from our oscillator strengths calculations, we find we get a radiative recombination rate of about 0.4 inverse nanoseconds, which is about on the scale of what's been reported in the literature by theory and experiment. So an experiment, depending on I guess it varies depending on the resolution of the instrument you have, but normally at room temperature they give between 1 and 10 inverse nanoseconds. And then recently there's been a big Nature paper that describes predicts radiative recombination rates based on size of the nanocrystals, and ours would fall into, I guess ours is even a little smaller than what they predicted. The lowest number they gave was like 4 nanometers, and they predicted that would be at about like, have a lifetime of about 1 nanometer, or not nanometer, nanosecond. So it falls within the same order of magnitude of what we compute. And so with this, we got a radiative rate, which we converted into a lifetime, which is 2.35 nanoseconds. And same for the non-radiative, we can plug it into our photoluminescence quantum yield, and we get a little bit lower than what's seen in experiment, even for like bad perovskite samples. So 33%, like you can initially make them for about 50%. So our computations are off a little bit, and that's mostly due to our non-radiative relaxation being likely overestimated a little bit. And one reason for this is it's been hypothesized that the Rashba effect slows down non-radiative relaxation across the gap due to it's kind of like you need a phonon-assisted spin flip, or you need not account just for energy across the gap, but you also need to account for phonon mode, which is I guess it's not a very strong effect for perovskite nanocrystals, but it could be enough to slow our rates down a little bit. And then for our cooling and our radiative rates, they fall within roughly the same order of magnitude as seen in an experiment. So, and then acknowledgements, haven't filled this in yet, but funding, primary one. And yeah, that is it.
Okay, let's thank Aaron. So, John and Braden, if you have questions, ask first, because connection can be broken in 3 minutes. They didn't expect.
It was hard to follow.
No, I'm good. Thank you.
Yeah, I'm good too.
Okay.
Could you again explain the difference, I mean not the difference, the way how you calculate the non-radiative relaxation recombination time, not relaxation, recombination time?
Recombination time? So I just come straight from the non-adiabatic couplings. Or once we process the non-adiabatic couplings.
But are you using like exponential feet into your data or anything? Because
that's what that rate is.
Huh?
That's what, yeah, that's a single exponential that we fit to the data.
So it's already include this single exponential behavior, which looks like.
It's an approximation.
I understand, but it's already showing the difference, like you'll show in the deviation between. Next slide.
This one?
Where you're comparing the exponential decay versus this one, right? So means you're already showing that actually it's not exactly exponential trend.
Right.
Is it also, but it probably depends on where you excite. But you said like it's the same features for your HOMO-LUMA transitions as well? Or this is only for the interband transitions?
So,
the used method for HOMO-LUMA transition will show literally single exponential decay, because between two states there is nothing else, at least in these approximations.
Yeah.
So what Aaron is reporting is not a fit to single exponential, it's just a rate. It's non-adiabatic coupling squared for
so it's
HOMO-LUMA transition.
So it's the number literally coming right out of our Redfield tensor.
So this approach
but
doesn't.
Can you really kind of use this estimation based on your dynamics without calculating the rates? But just knowing your non-adiabatic couplings, right, and kind of fitting it with exponential, and just using the fitting function and check how the k new exponential function will be agreeing or not agreeing with this Redfield tensor.
It can be done, but in some sense, all this processing of non-adiabatic couplings is included into this M symbol. It's basically average of non-adiabatic couplings along the trajectory.
Oh, okay.
More questions? There is a hope that there were some written questions on the
I have another question. I was lost somewhere. You said that you calculate your couplings with including the spin orbit couplings, right?
Yes.
But do you have calculations without, like, and somewhere in your conclusions you're saying that the rates would be faster if you include the spin orbit, but you already include the spin orbit. Or Rashba effect, whatever this effect.
So what is needed to, you do have spin orbit, but you do not have Rashba.
Right.
Then I don't understand what is Rashba effect.
So Rashba effect is, it's coupling, like if you have a charge if you don't have equal to like charge distribution, like in your crystal, it's going to create some sort of magnetic dipole, and that couples with electronic structure. I guess I don't know the exact mechanism.
So kind of induced magnetic field.
Yeah.
And the
that couples with the
spinning
spin.
effect was
Yeah. So basically what it, like, I can draw a picture of it.
Mm-hmm.
So. Like,
But why
that's-
is it? You said that this Rashba effect would increase. It would
decrease?
slow down
It should
the.
slow down. Because if this is usually like your dispersion band, what Rashba effect does is it splits, makes it spin dependent. So if this is like your spin up, and then spin down. And it does that for both bands. So, and I think it like switches the spin indices too. So you would need a,
You're gonna find an additional channel.
right.
Huh.
So you need a little additional energy corresponding to the splitting of your momentum,
I see.
which we might be able to do one day since Fatima figured out how to do couplings between K points.
Yeah, for Rashba one needs K points. So we need to put together both spin orbit and K points.
It's a fancy
But
title.
you also have calculations. You didn't show it, but I remember your previous calculations. You also have your dynamics without spin orbit coupling, or you
Mhm.
don't.
I do.
Like just with how it calls spin fixed, spin
Restricted.
restricted.
call.
Yes. So and then your rates. How much then they are different? Spin versus no spin.
I think.
Especially if we, I remember you changing the band gap significantly with the spin orbit coupling, right?
Band gap changes, I think the cooling rates, they're same order of magnitude. They're like factor of 2, factor of 4 different.
Slow.
By some
I
reason,
think-
with spin orbit it gets slower, right?
I'd have to double check. It's been a while since.
But this is kind of interesting. I would definitely add this. You don't need to really make a big kind of discussion on it, but somewhere at the end you can compare these results with your spin without spin orbit and spin orbit,
Mm-hmm.
right?
Yeah, that's a good idea. I just couldn't find a natural way to put it in. But I guess I can.
Very
You
natural.
can
Just
put
say like,
backup
and
slide.
if we like you can for mention our main feature is including spin orbit. If someone neglects spin orbit coupling, then so here is a calculation done without this, and we see the very significant, significant, not significant, twice or 3 times difference, right?
Mm-hmm.
Either this way or that way.
Mm-hmm.
Which again probably brings a very important conclusion to your final conclusion that you really need spin orbit calculations for getting this accurately.
Yeah, I think the biggest thing, or the biggest difference would be this feature here, if we could actually see it.
Mhm.
So it's without spin orbit, you have a denser amount of states near the band edge, where with spin orbit it's like 0.1, 0.2
More
EVs between.
splitting, right?
Yeah, so your decay is going to be different. So it's going to be faster near the band edge for the electron for spin restricted compared to spin orbit.
And again, you might add the line here if you have it, or just maybe some data, just numbers, right, for the rates or something like this.
Mm-hmm. Yeah, that's a good idea to just put it into here.
Or average non-diabatic couplings up to like there are either rates or couplings or really kind of illustration for quicker bands.
Mm-hmm.
I mean for quicker ages of this curves.
Mm-hmm. Well, that definitely makes sense. Does it make sense to do PDOS with this?
I didn't get it at all.
I got it, but it is not self-evident.
Yeah.
Yeah.
And plus I'm confused what is your x-axis in this case?
So it's time.
Energy?
So it's time.
How's and time is negative? Oh, it's log.
Log time. Log time.
Ah.
Yeah, the axis got cut off. So
Is
it's
it,
log.
is it a reason to put time in a log format here?
There
If
is-
it's really straight lines, you can just make it like nothing really happens.
what would be much
You can just
easier
make
to,
a big
much more
jumps.
digestive is instead of putting
Your call will be disconnected.
-3, put
Bye bye guys.
bye John, bye Brian. So you can put instead of -3, put there 1 picosecond. Instead of -2, put 10 picoseconds. Instead of -1, put 100 picoseconds, or femtoseconds. Where you have 0, put 1 picosecond.
Like
So
you still,
it
you
is
have
still
log of time,
log scale,
but
but
you scale
will
it
be
not 1 to 3, but actual time
Mhm.
scales.
Since, yeah, it's kind of hard to resolve on there because it's such a low. But for the PDOS I was talking about, maybe I would just have to zoom in on the carbon oxygen.
I mean, I understand that you're making an important point, but honestly, I completely miss it. Like, how exactly this representation explains this deviation from exponential curve? I mean, I got the main message, but I was lost in the details. Like, how exactly it works, I didn't get it.
Yeah, so this is more just like a correlation. Like I would need like the spectral density to show that there's this vibration happening here, and you can see it's causing dissipation of this carbon density.
Put
But maybe-
equation. How did you compute it? Like,
Why not
okay,
put the phonon spectra? Right?
I mean-
You can also prove it with spectra of phonons, right? To show that you have these phonons contributing, this CC over whatever stretching phonons contributing there,
Yeah, that's what I was trying.
coupled.
Yeah, that's what I was trying to get for the presentation, but I don't know, I was struggling, so I just.
Oh, you don't have
Process
the,
this stuff.
you don't have. Like
how many atoms and how many electrons do you have in your system?
1,000 atoms and like about 3 or
But you just do
2,500
Fourier
electrons.
transform and see where the peaks. Like, have you done Fourier transform of your trajectories electronic state?
I've tried, but I couldn't get the data, or I couldn't make sense of the data I got.
So like you're getting no peaks, you're getting something like completely
Yeah, it seems kind of like noise. I couldn't.
noise without really clear peaks.
So I have to play with the Fourier transform parameters. Try to make sense of it. But I mean, it has to be there because you saw in the image. Like right away, there's density, right, 2p coming out of the carbon atom. So there's got to be at least a little bit of coupling from one of those stretching vibrations.
So maybe Aaron needs to practice once again, and since there will be more posters to be printed on not tomorrow but coming Wednesday, right? And since your presentation is not a poster, you can practice on Friday just before departure. Last Friday before the meeting.
Mm-hmm. That works.
More questions to Aaron?
The total time was around 28, 29 minutes.
Oh, just shorter twice.
Well, there were some interruptions due to the
I excluded some
technical
instructions.
problems.
You know you can make screenshot for each your slide and make your slides uneditable, just as one big figure, bitmap figure that not of several objects but screenshot on each slide, and then it's guaranteed that it will be seen on any system.
I'll have to do that for next time.
And this is supposed to be a movie, right? For the slide which you just
Yeah,
showed.
but the movie did work. The movie worked. Well, on this computer anyway.
It was?
The movie did work, yes.
Something was moving?
Yes. Oh, play the movie once again.
What exactly was moving?
And index with your finger.
I see the numbers are changing, but I don't see anything is moving.
Time is updating, so
No, I
take a
understand
look.
this, but what is really moving in a movie?
So
Is
one
that-
electron is migrating from the lead p orbitals to in another adjacent p orbitals on this state. And then you can see for the blue, those are the holes. So you can see over time they like this bromine p.
So they increase in blue, they becoming more blue or what?
Yeah. So the darker the color, the more intense the population.
I didn't see. Anyone?
Yeah.
So there's not a lot of
You were
color.
able to see? Wow.
Is a color changing there?
So you can see like very dark. That's like highly populated because that's our initial condition. So everything's kind of contrast to that. So it's not as dark. But so you see electron density leaving.
You really need to follow because if I'm looking on the wrong atom, nothing is happening.
Mm-hmm. Well, if you look at the center one, something eventually happens.
Okay. Okay. I don't know why I was looking really on the bottom line. Nothing really happens with the bottom.
So you can tell it without hesitation, like, I invite everyone to carefully focus on this.
No,
corner.
and I also was expecting that you really will show the thermal motion of your lattice,
Oh, okay.
but no,
Well, you can put it on your title slide while you are introducing who you are and what are you doing. It may play on the background.
Yeah, that's a good idea.
For entertainment.
Mm-hmm.
done?
More questions one, more questions two, more questions three. Thank so, give him feedback if any, and many thanks to everyone for contributing to the meeting and discussion. Meeting is dismissed. See you on Friday.
And who is presenting on Friday? According to the schedule, anyone remember?
Is
No?
for poster print.
Is it Ben? According to our old schedule. No?
I don't.
Jabet, did you present on your research update?
No.
My one is following week, I guess.
Okay, let's figure it out and distribute an email.